Today we're going to have a look at power functions. Now, here we're referring to functions that are of the form f of x equals x to the n. So some of these we already know, like y equals x is easy enough, and we might often know x squared, x cubed. We're talking about the very base functions here, where it's just x to the power of a number. Some of these are a little less obvious, such as the square root of x being x to the power of a half, or the third root of x being x to the power of a third. So in general for this video, we're going to be looking at case 1, where n is a positive odd integer. So we're looking at x cubed, x to the 5, x to the 7, etc. We'll also look at it where x to the n, where n is a positive even integer. So x squared, x to the 4, etc. We're then going to have a look at the negative numbers of these. So x to the negative 3, x to the negative 5, also looking at x to the negative 4, x to the negative 6, and finally we'll finish off with the fractions, x to a half and x to a quarter and x to an eighth, all being the even fractions, and the odd fractions, x to a third, x to a fifth, x to a seventh. So starting by looking at x to the n, where it's a positive odd integer, we note that these will always resemble a cubic function. Now we're just interested in the very basic form here with a point of inflection. You may remember that from 1-2 methods. So over time, as x increases, the graph will increase. And so it's pretty fair to call this an increasing function. We're going to do a lot more of that when we get into calculus. So for now, it's enough just to remember that phrase. We're going to think about these functions in 3 different sections. So one of these sections, we might think about what happens in between -1 and +1. So that is when we sub in values that are generally considered fractions, something like -1/2, +1/3, etc. We then want to think about how do these functions behave if we're subbing in values bigger than 1, so everything to the right of that, and we might also consider what's happening to the left, so everything that's less than -1. Whenever we're interested in drawing power functions, we're really thinking about what are they relative to one another, because we know they have the same general shape. So imagine we subbed in something bigger than 1, like the number 2. Well, for my y1, if I had 2 to the power of 5, then I know that that's 32. Relative to my y2 over here, 2 to the power of 5 is going to be 512, to the power of 9, I mean to say, sorry. So at those points and everything bigger, I can think that everything past 1, such as the number 2, is going to rise more rapidly with x to the power of 9 than with x to the power of 5. You might also have noticed that if I sub in the point 1, I'm going to get the value 1. And likewise, 1 to the power of 5 is also 1. So we've got a point of intersection here at 1, 1. Just make this a little bit thicker so that's easy to see. I know that as this extends, it's not going to be as rapid an extension as x to the power of 9. This works also when we sub in negative values. If I subbed in -2, well, -2 to the power of 9 is -512. -2 to the power of 5 is only -32. So at that point of intersection at -1, because again, -1 to the power of 5 is -1, and -1 to the power of 9 is also -1, I know that my x to the power of 9 is going to decrease more rapidly than my x to the power of 5. So the question becomes, what happens inside this range of -1 to 1? Because if there's a point of intersection, it means that the lines had to have crossed over. So that means that here I'm quite a bit more flat. And if it crossed over, that means that I need to get closer to 0. So I'll sketch these out a little bit better and we'll explain what's going on. So imagine we subbed in something in between that range of -1 to 1. Well, if I sub in a half to the power of 5, that's like saying 2 to the -1 to the power of 5 or 2 to the -5. So we know that a half to the power of 5 is 1 on 32. It's quite a small fraction. But it's not nearly as small as a half to the power of 9, which is 1 on 512. So I know that in this section here, my black line should be closer to the x-axis because it's going to be a smaller fraction. It's really important that we still have our point of intersections labelled though. So whether I've subbed in 1 or -1, these are going to represent points of intersection. And we also know that 0 to the power of 5 or 0 to the power of 9 represents a point of intersection as well. So again, thinking about the sections that we started with, anything that's in this purple section here, so we can think of it down there, I should see that the black line is below the blue line, or rather it's approaching negative infinity a little bit quicker. Anything that's to the right of 1 over here, I should see that the black line is above the blue line because it approaches infinity quicker than x to the 5. Now the interesting thing is that anything in between that section there, well, you can see, if we highlight it, that the black line actually approaches 0 quicker. And so it's with fractions in between the value of -1 to 1 that the rate of increase here actually swaps over. That's really important to demonstrate in your graphs if you're ever graphing x to the 5 and x to the 9 on the same axes. Let's now look at the case where x to the n being an even integer. Well, we know that these resemble a quadratic function. In fact, if you think back to 1-2 methods, you knew that x squared looks like a parabola, and x to the 4 just kind of looks like a more flat version of that. Again, we're going to think about this in 3 sections. So we'll start with all the values that are less than -1, all the values that are greater than 1, and then let's see what's going on in the middle here. Start with my first graph, x to the power of 8. If I choose the value of 1, well, 1 to the power of 8 is 1. And likewise, -1 to the power of 8, being an even function, is also 1. So that means that I've got a point here, 1, 1, and another point there. You've probably seen by now that if I did 1 to the power of 10, it's 1, and -1 to the 10 is also 1. So once again, these represent our points of intersection. There's another point of intersection also at 0, because 0 to the power of 8 or 0 to the power of 10 is 0. So we can put that one just there on 0. If we look at the shape of our general graph, that 0 point also represents our turning point. So let's think about what happens when values are bigger than 1. Well, 2 to the power of 8 is 256, and 2 to the power of 10 is 1024. If I subbed in a negative value, being an even function, this will also yield 1024. If I sub in -2, I still get 256. So we see this kind of reflection happening. 1024 is above 256. So as I'm sketching these graphs, I need to demonstrate that this almost goes directly up, and my blue line, my x to the power of 8, is not quite as sharp an increase. I'll just fix that arrow there. So let's look at that super interesting bit, because I know they both go down to 0, but what's going to happen between -1 and 1? Easiest value I can pick here is a half once again. A half to the power of 8 is going to be 1 on 256? That's because we can think of a half as being equal to 2 to the negative 1. So thinking of it this way, I can see that this is 2 to the negative 1 to the 8, which is 2 to the negative 8. Likewise, the same principle, a half to the 10 is 1 on 1024. Now this is a fraction that's much smaller than 1 on 256. So after this point of intersection, we need to really flatten out because we're quite close to 0. The blue line, on the other hand, is now on top, still a little bit flat, but not quite as much. It's important to label our graphs. So we'll do that now. Label our axes. Make sure we've got arrows on the endpoints. And we'll make sure we've labelled these points of intersection. So here we can see that we've clearly demonstrated the difference between x to the 10 and x to the 8, even though they both have the same general shape. Now what happens when n is a negative odd integer? So we're talking here x to the negative 1, or x to the negative 3, or x to the negative 5. You might remember x to the negative 1 is a hyperbola. So that's our general shape. If we think about what happens with numbers bigger than 1, and if we remember that we're going to have points of intersection here at 1, negative 1, 0, 0, and 1, 1, you can find those by subbing them into the graphs. Let's look at y equals 1 over x with a number like 2. Clearly, my y1 is going to be equal to a half when I sub in 2 for x. My y2, on the other hand, if I sub in 2, will be 1 over 2 cubed, or 1/8. So as I sub in bigger numbers, or rather numbers that are to the right, so remember we did that as a green section, I need to get closer and closer to 0. So it's important to make sure I can demonstrate that here. It's also important as I sketch this graph that I never cross the axes, because we know we have y equals 0 as our asymptote. So in fact, I think I mentioned before that 0 was a point of intersection. It's definitely not. If I subbed in negative values for this, something like negative 2, well, we'd get negative a half. Subbing in negative 2 into x to the power of negative 3 gives me negative 1/8. So again, from this point of intersection, I need to get quite close to this asymptote. And that would be different to the case here, where I'd have a slower approach speed for my blue line. We can put that in here. Now, with these values, we know that we had a point of intersection, so they have to physically cross, which means that now my blue line is going to be closer to the y-axis. And my black line, which had to cross over, is going to approach that at a slower speed. And this can be a difficult one to see, but if you remember that the lines have to cross here at 1, 1 and negative 1, negative 1. We've got an asymptote at x equals 0 and one at y equals 0. We might as well label the x and y axes. As long as we've shown that they're both approaching the asymptotes and that they do so at different speeds in different sections, we should be okay. When we have the case of an even negative integer, so we're looking up here, we know that that represents the general shape of a truncus. So that's the one that looks like this. Again, if we think of it in terms of numbers that are bigger than 1, numbers that are in between negative 1 and 1, and numbers that sit more negative than negative 1, or to the left, this provides a good idea for our shape, or at least our relative shape. We know that a truncus has an asymptote at both x equals 0 and y equals 0. So we can start by putting those in now. We know that if we subbed in 1, let's take the first graph 1 over x squared, well, 1 over 1 is 1. So I've got a point here. I also know 1 over 1 to the power of 4 is still 1. So that's a point of intersection. If I sub in -1, well, that's going to be 1 over -1 squared, which is 1. And if it's -1 to the power of 4, that should have been black there. There we go. We know that that's also 1. So we have this kind of reflected point of intersections at 1 and -1. So let's see what happens to the right of 1. If I subbed in 2, then y equals 1 over 2 squared, which is a quarter, relative to y2, which is 1 over 2 to the 4, which is a 16th. I know that 1/16 is a lot closer to 0 than 1/14. So in fact, to the right of this point here, we're going to approach really quickly. And the graph of 1 over x squared will not approach quite so quickly. Again, to the left, we're going to approach real quickly. And the truncus, or 1 over x squared, will do so a little bit slower. Now, remembering that these have crossed over, we can still do the math and double check it. What happens if I sub in a half? Well, if I've got y equals 1 over a half squared, that's 1 over a quarter. So how many quarters go into 1? 4 do. By the same principle, if I take y2 equals 1 over a half to the 4, I get 1 over a 16th. And how many 16ths go into 1? 16 do. So I know that 16 is much bigger than 4. So at this point I have to show that, well, that's going to approach a bit slower because it shoots off quite high pretty early on. And my blue line gets much closer to the asymptote much sooner, which is what we might expect because it is a point of intersection, so the lines do have to cross over. Labeling what we have, making sure I've got the asymptotes in play. I don't have to label them over the axes, but sometimes you may want to do so. And ensuring that we sketch first graph, which is y equals 1 over x squared, and the second graph, y equals 1 over x to the 4. Okay, so we're getting there. What happens now if we had 1 on n, or rather a fraction that was positive and even? So let's consider something like x to the power of a half, which is a square root function. We know that a square root function starts at 0 and shoots off like that. The important thing to recognize here that if it's an even root, we can't have the even root of a negative number. So the case that we were considering of, everything kind of to the left of -1, certainly we don't have to worry about that. And we also don't have to worry about 0 to -1. We can't do the square root or the even root of a negative number. So we know we have a point of intersection at 0 because the square root of 0 is 0 and the 6th root of 0 is 0. So that makes sense. We know that we have a point of intersection at 1 because the square root of 1 is 1 and the 6th root of 1 is 1. So we now need to consider two cases. What happens to the right of here and what happens to the left? Let's start at the number 2. Well, y2 equals 2 to the power of a sixth, which is the sixth root of 2. And if I consider the square root function, well, y1 equals 2 to the half, which is the square root of 2. We might be thinking, what's bigger, the square root of 2 or the sixth root of 2? And I'm hoping that you'd realise that the square root of 2 is bigger. So what did I have to multiply by itself to get to 2 is surely bigger than something that I multiplied by itself, and then itself again, and again, and again, and again, and again, and then I got 2. So here, at all things that are to the right, I would expect that the square root function is actually going to be a little bit higher up than the sixth root function. So the square root function, you might think of it as rising more rapidly. Now what happens if we had a fraction? Well, we get the opposite of this. The easiest way I can explain that without going too much into the arithmetic is that we've just had a point of intersection. So I need to demonstrate that it crossed over, and so whichever function was on top should have swapped. If we label it correctly at 1, 1, label our axes and also label our graphs. These are some of the easier ones we get done. So we know we can't have the square root of a negative number. Indeed, we can't have the even root of a negative number. But what happens if we had the odd root? Well, that actually does work, just like -1 cubed is indeed -1. Now, when we have a positive odd integer, as we see here, we're saying that functions like this will resemble a cubic on the y-axis. So imagine that you had a cubic, but then you rotated it 90 degrees. Well, then you'd get something that looks a bit like what we might call an S-curve. It's a little bit like a stretched out S. So the function that we're looking for here has this shape. Once again, being a square root function or acting very similar to that, we know that we have -1, -1, 0, 0, and 1, 1. You can sub in these values and check them yourself. Let's think about what happens if I sub in a bigger number. Well, if I subbed in something that was bigger than 1, so let's say y equals 8, well, I meant to say x equals 8, then we'd know that y equals the third root of 8, or 8 to a third. And that number is physically 2. If we subbed in that same value for x, the third root of 8, this time it's not the third root, it's the seventh root, we can see that the seventh root of 8 is a number that's just that little bit more than 1. So without a calculator on hand, I'm going to estimate that that's about 1.17. Pretty decent guess, it seems. The only important bit here is that we can note that that's certainly less than 2. So to the right here, we're going to approach things a lot slower. That's also true after the left. We're going to approach things much slower. Now we note that 2 is a little bit bigger, so we've got to end up above this line, and -2 would be a little bit lower, or more negative, so that had to be above that line. Now if the blue line was the bigger line in this case, or the one that's further away from the axes, then after we've crossed, we should see the opposite effect in play. So I'm just going to sketch these graphs a little bit more clearly because the shape is a little bit askew. There we go. And remembering that we have to make these points of intersections physically cross over and and again cross over, that kind of shows us that with those fractional numbers, we get the opposite effect. Labeling what we have, we've got 1, 1, -1, -1, and 0, 0. Everything else obviously should be labelled accordingly also. Now what we've used as examples here, 1/3 and 1/7, could be used with any set of different numbers. It could be used with a 5th and a 9th, or it could be used with a 9th and a 13th. All we have to know is that the power that is higher will follow the same pattern that we've looked at today. This summary section from the Cambridge text, and I think this is at the end of 1G, is a fantastic way to visualise all the different types of power functions we might get. So we know that if it was an odd positive number, as we can see here, it's going to look just like a cubic. An even positive looks a bit like a quadratic. An even negative, a bit like a truncus, the odd like a hyperbola, and then the even and odd root functions are kind of like their own beast. It's really important that we know the relative differences though, and that we're able to sketch x cubed and x to the 7 on the same set of axes.